we are going to do facial recognition using principal component analysis. So our eigenface implementation, if we had a set of training images, we should use we should eigenface each training set. That is, if we had 5 facial images of Dewey, 5 of Gabby, 5 of person P, we should actually do a mean face for each of them, and then use that as our known. To match, we will use the nearest neighbor classification between test image against everyone else's mean face. Okay. Here we will use mean face of all training images combined and get the K principal components. We will project all known faces into PCA space, project test face into principal component space, and then pairwise compute Euclidean distance between each known and test projection, and then we will match minimum via Euclidean distance. So here we will load the training images, and then we will read all of it, and then we will flatten each image into a row vector. So that's this image right here. We will slice it row-wise, and then we will stack it into this row thing. And we will do that for training images, we will do that for known images, and then we will do that for test images. For known and test images, we will also read the file names so that we know what we were matching up to. And then here, this is just some code to remove the prefix of the file name. So we're just removing like the front part of the name, and then we will get left with this down here, just the last part of the file name. And then for each data matrix, each row of an image, we have a grayscale. So a grayscale point in 1024 dimensional space. So 0 is black, 255 is white, if you don't know what grayscale is. And we will convert each cell to matrix for train, test, and known. Okay, so that's this slicing thing right here. Oh no, we were creating a data matrix. So when you first import it, you actually get a list of vectors, and then we will convert it to a matrix. So that's what this is right here. Train. Where's our train? Yeah. So if you look at this, we will actually have a list of vectors. So we don't want that. That's what this line of code does. And then we will compute the mean image, and then we will subtract it from everything. So right now we have 35 training data points in 1024 dimensional space. Okay, so I know this is 2D, but I can't draw 1024 dimension. And then we will subtract the mean face from it, and what that does is that will center all of our data points. If all of our data points are centered, then we can actually consider each tip of each data point as a tip of a vector, and that's what we want because we are going to do principal component on it. So we will do dot product between each pair, and that will give us the correlation. So principal component, you actually have to standardize it, but standardization is actually not performed there because it is redundant. Everything is already on the same scale, and when everything is already on the same scale, the covariance matrix is actually the correlation matrix. And here is the proof right here. Yeah, so is the covariance of the standardized variables also the correlation? And the answer is yes. And here's the proof. Link is in the description below. All right, so back to our principal components. We compute the mean image, and then we can actually put it back together right here. So we will we will reshape our row vector into the matrix vector. So it should be a 32 by 32, and then we will have a matrix, but we want to change it into an image. So we use matrix to grayscale, reshaped, and 0 is black, 255 is white. So when we run this, we actually have a pop-up of the mean face. So this is the average face of our training data that we subtract to center our data points so we can treat them as vectors. Now we can, okay, next step right here, we will coerce them into double so we can actually do calculations, because right now they're just integers. We want to turn them into double, and then this subtracts the mean face from all of our folders, and that gives us this. This is what we want. And then we could have used covar function, but I actually used the formula. So this is the formula for covariance matrix, and you can see it's just A dot A divided by N. So what that does is you have every pair of vector, you project it on to the other pair. And this is actually symmetric matrix because it inherits commutativity from the real numbers. So we have a product of A equals B, A times B. So A times B equals B times A. That's the commutativity product property of real numbers. A plus B equals B plus A. So that's why you get a symmetric matrix, the covariance matrix. Next, we do spectral decomposition. So because we have a symmetric matrix, we can actually do spectral decomposition. So if you don't know what it is we take the covariance matrix and then we rewrite it as Q diagonal Q transpose. So Q is actually the matrix of eigenvectors, all right? And then the diagonal matrix is actually our eigenvalues that correspond to the eigenvector. So this is eigenvector 1 corresponds to eigenvalue 1, eigenvector 1 transpose. So we can actually, if you actually check this out, this is actually not orthogonal, but we can orthogonalize it by using Gram-Schmidt process. So the Gram-Schmidt process allows us to transform linearly independent vectors into orthonormal vectors, and we know eigenbases or any set of basis vectors are by definition supposed to be linearly independent. So it transforms it into a rotation. So we rotate from standard basis onto our orthonormal eigenbasis, okay? And then we actually scale each eigen basis up by its eigenvalues. And that's what spectral decomposition does. And then it also rotates it back. So when you look at this right here, you see that the vector is on the right-hand side. So we're doing a right multiplication of a matrix. So we do the calculations. Because we write left to right, we have to perform our transformations from right to left. That's just a consequence of how we write. So we actually have this comes first, and then we do this, and then we do this. So we rotate our standard basis vectors onto our orthonormal eigenbases, and then we multiply each eigenvector by its corresponding eigenvalue, and then we rotate our eigenbases back to eigenvalues. So you kind of get this right here. And so if we double click on this, you see the diagonal, and then you have the eigenfaces. I'm calling my eigenvectors eigenfaces. And this right here, if you double click on it, you will see that it is our eigenvalues in non-increasing order. Okay, so we're just calling the largest 50 because I want to do a dimension reduction. I don't want to use all 1024 dimensions. We want to reduce it to the top 50 eigenbases. And now we will project each known that's already centered onto the eigenfaces. So here is our known data. We have 12 rows of known, and then it is 1024 wide. That is how many pixels are in each. And then we were going to multiply it with the eigenfaces. So this is what it looks like. And this is our projected node. This is what our matrix multiplication is doing. And here's the formula. And as you can see, it is actually the dot product. This is just a container holding all of our dot products for our projected known and our projected test. Okay, so that's what the matrix multiplication is doing. Next, we want to get the size. This is just some boilerplate code, and then we're gonna initialize a distance container. It is initialized as 0 for now. This is just how big our test matrix is along the row. This is how big our known matrix is along the row. You can take a look at the numbers right here. But this is what is important. We will calculate the Euclidean distance, which is also the L2 norm. So this is the formula. So we are taking the projected known I, and then we're going to subtract projected test J, right? And then under the hood, what it's doing is taking the projected known 1 subtract projected test 1, and then we're going to square it, and then we're going to add up all 50 of them, and then we're going to square root it, and that gives us the Euclidean distance. And then you can see right here our projected known. We have 50 columns because that's our how many principal components we have, and then it is 12 tall because that is how many known images we have, and then we have 23 test images. So projected test is actually 23 tall and 50 wide, and this is like the dot product if you want to take a look at it. And then after we find the nearest neighbor, we actually save it. So what that does is it takes the distance matrix and it row-wise sweeps across looking for the smallest value. When it finds the smallest value, it comes up and look at the column, and that's actually the J index. Initially, I just used numbers, but then I found out that we actually have to have the file names. So that's why I added this right here, the file names, and then we had to strip the all my computer folder names and stuff like that. Yeah, so we strip that off, and then we match up the row number and column number to its corresponding file names. So that's what this loop does. And then afterwards, it just prints out this right here. So test face 131 is closest to known face 131. So that is correct. Then there's like some other ones that are incorrect. So we actually have 17 matches out of, 23? So a match count divided by 23, and my accuracy is 73.9. And we can like kind of play around with like the K. That is how many dimensions we're keeping to see if we can get better values. Where is that line of code? K. So let's make K 150. All right, and I'm gonna run it, and no better accuracy. There's the mean face again. So I mean, if I'm gonna get the same result with 50 as I will with 500, I might as well just keep it at 50. No point in like wasting all that computing power and not get anything better. And that's it for this video.